welcome to this problem walkthrough. In this session, we'll tackle problem number 1439, find the kth smallest sum of a matrix with sorted rows. This is an interesting and challenging problem where we'll explore methods to efficiently compute the kth smallest sum from a matrix with sorted rows. Let's dive in and explore the solution approaches together. In this problem, we are working with an mxn integer matrix called mat, where each row is sorted in non-decreasing order. The task is to find the kth smallest sum that can be formed by selecting one element from each row of the matrix. To clarify, you are allowed to take exactly one element from each row, sum those selected elements together, and then determine the kth smallest sum out of all possible combinations. Inputs include the matrix mat and an integer k, while the output will be a single integer representing the kth smallest sum. For example, if the input matrix is 1, 3, 11, 2, 4, 6, and k is 5, the output will be 17. To understand why, we calculate all possible sums by selecting one element from each row. For instance, adding the first element of row 1, which is 1, to the first element of row 2, 2, gives a sum of 3. Continuing this process, other sums include 5, 7, 9, and so on. Once all sums are computed, we sort them in ascending order: 3, 5, 5, 7, 7, 9, 13, 15, 17. The kth, or fifth smallest sum in this case, is 17. Now consider an example where the input matrix is 1, 3, 11, 2, 4, 6, 5, 6, 7, and k is 9. This time, we again calculate sums by selecting one element per row. For instance, picking 1 from the first row, 2 from the second, and 5 from the third gives a sum of 8. Similarly, 1 plus 2 plus 6 equals 9, and 1 plus 2 plus 7 equals 10. There are many such combinations, and once all sums are derived and sorted, the ninth smallest sum turns out to be 17. In another example, if the matrix is 1, 10, 10, 1, 4, 5, 2, 3, 6, and k is 7, the output is 14. Here, there are numerous possible sums, and after sorting all of them, the seventh smallest sum is 14. This example demonstrates the importance of efficiently generating and sorting sums, especially when the matrix has multiple rows with varying ranges of values. This problem comes with some constraints and edge cases that must be considered. The matrix can have up to 40 rows and 40 columns, and the values in the matrix can be as large as 5,000. The value of k is capped at the minimum of 200 or the total number of possible sums. Edge cases include single row or single column matrices, and scenarios where k approaches the total number of sums, requiring optimized computation. Brute force approaches become infeasible as the matrix grows, highlighting the need for a min-heap or priority queue to dynamically track the smallest sums. By leveraging the sorted property of rows, we can efficiently generate and manage the next smallest sums without exhaustively computing all combinations. To address the problem of finding the kth smallest sum of a matrix with sorted rows, we first explored multiple approaches. One straightforward method is the brute force approach. Here, we generate all possible sums by selecting one element from each row, sort these sums, and return the kth smallest. This method capitalizes on the fact that the rows are sorted, making it conceptually simple. However, the time complexity grows exponentially at n to the power of m, where m is the number of rows and n the number of columns. This makes it infeasible for larger matrices. To overcome this, we considered an optimized approach using a priority queue, or min-heap. In this method, we begin with the smallest possible sum, which is formed by taking the first element from each row. We then iteratively replace the smallest sum in the heap with the next smallest sum by modifying one element at a time. This process is repeated k times, allowing us to efficiently track and retrieve the kth smallest sum. The intuition here is that using a min-heap systematically generates sums in ascending order, similar to finding the kth smallest element in a sorted array, but applied to combinations of rows instead. The time complexity of the min-heap approach is k log k. This accounts for k iterations, where generating new sums involves m operations and heap manipulations are logarithmic. This makes the method computationally efficient for larger matrices, as it avoids creating all possible sums upfront. Another approach we considered is binary search with row-wise combination. Here, we use binary search over the range of possible sums. For each candidate sum in this range, we dynamically combine rows to count how many sums are less than or equal to the candidate. This allows us to determine if the candidate could be the kth smallest sum. Binary search significantly narrows the range of possible sums, making it efficient. However, the time complexity here is O, m*n*log, max_sum, where max_sum represents the maximum sum possible. The added complexity of row-wise combinations makes this approach more challenging to implement and debug compared to the min-heap method. While efficient in theory, it demands careful handling of edge cases and dynamic constraints. After evaluating these methods, we chose the optimized approach using a priority queue, or min-heap, as our solution. The primary reason for this decision is its simplicity compared to the binary search method and its efficiency over brute force. With a time complexity of O, k*log, k, the heap-based approach scales well even with larger matrices. This method avoids the need to generate or store all combinations of sums, making it memory efficient. A key insight that guided this choice is the fact that the rows are sorted, which allows us to systematically explore sums in ascending order. By leveraging a min-heap, we ensure that the smallest sums are always processed first, aligning perfectly with the problem's requirements. Additionally, dynamically generating sums rather than pre-computing them significantly reduces the computational overhead, making this approach both practical and optimal. When comparing the three approaches, we see clear trade-offs. The brute force method is straightforward but quickly becomes impractical due to its exponential time and space complexity. Binary search, while efficient in narrowing the range of possible sums, introduces additional complexity in implementation due to row-wise combinations and is slightly less efficient in some cases. The min-heap approach strikes the best balance between simplicity, efficiency, and scalability. It avoids the pitfalls of brute force by dynamically generating sums, and it is easier to implement and debug compared to binary search. In conclusion, the min-heap approach is the most practical and optimal solution for this problem, adhering well to both time and space constraints while ensuring correctness and scalability. In this problem, we are tasked with finding the kth smallest sum that can be formed from a matrix with sorted rows. The matrix has m rows and n columns, where each row is sorted in ascending order. To solve this, we need to select one element from each row and compute their sum. However, instead of generating all possible sums, which would be computationally expensive, we aim to determine the kth smallest sum efficiently. To achieve this, we use a priority queue, also known as a min-heap, which enables us to process sums in ascending order. This approach ensures that we focus on the most promising sums without generating them all up front. To break down the algorithm, we start by initializing the heap with the smallest possible sum. This is achieved by selecting the first element from each row, and we store this sum along with its corresponding state. The state is represented as a tuple, where the first value is the sum, and the second value is a list of indices indicating the selected elements from each row. For example, if the first elements of the rows are 1, 2, 3, the initial sum would be 6, and the state would be 6, 0, 0, 0. Next, we perform heap operations. We extract the smallest sum from the heap, which is guaranteed to be the smallest unprocessed sum. For each row, we create a new state by advancing the index for that row, calculate the new sum, and push it into the heap. To avoid redundancies, we maintain a visited set to ensure that each state is processed only once. The process continues by repeatedly extracting the smallest sum from the heap and generating new states until we reach the kth smallest sum. The heap's property of always extracting the smallest element first allows us to efficiently track the order of sums. By using state representation, where each state includes the indices of selected elements, we avoid generating all possible combinations up front. The visited set plays a critical role in ensuring that we do not process the same state multiple times, preventing unnecessary computations. This optimized search approach leverages the heap structure to limit exploration to the most promising states, making the algorithm significantly more efficient than a brute force method that explores all combinations. The two primary data structures used in this algorithm are the min-heap and the visited set. The min-heap stores sums along with their states, and its logarithmic time complexity for insertion and extraction makes it ideal for this problem. The visited set tracks already processed states to prevent duplicates, ensuring that each state is processed only once. Each state is represented as a tuple containing the current sum and the indices of selected elements from each row. In terms of complexity, the time complexity depends on the number of states we process, which is k. Each heap operation takes O log k, and for each state, we generate up to m new states. Thus, the overall complexity is approximately O k m log k. For space complexity, both the heap and the visited set store up to k states, resulting in a space complexity of O k m. Finally, let's address some edge cases. If the matrix has only one row, the problem simplifies to finding the kth smallest element in a sorted array. If k exceeds the total number of combinations, which is n raised to the power of m, the problem is invalid, and we must handle this case. If all rows have only one element, the result is simply the sum of those elements. For matrices with duplicate elements, the visited set ensures that duplicate sums are handled correctly. As an example, consider the matrix 1, 3, 5, 2, 4, 6, with k equals 4. The initial sum is 3, formed by selecting the first elements of each row. After extracting 3, we generate new states by incrementing indices for each row, such as 4, 1, 0, and 5, 0, 1. This process continues until we find the fourth smallest sum, which is our result. This demonstrates how the algorithm efficiently navigates through the solution space to find the desired sum. This implementation solves the problem by using a heap-based approach to efficiently find the kth smallest sum of a matrix with sorted rows. Here's a detailed line-by-line explanation. 1. Imports. The heap module is imported for heap operations, which are used to efficiently manage the smallest k sums during processing. 2. Class definition. The solution class is defined, containing the method kth smallest to solve the problem. 3. Helper function. The merge_sorted_sums function merges two sorted lists of sums while maintaining only the smallest k sums. It iterates over all pairs of sums from list 1 and list 2, pushing their sum into a min heap. If the size of the heap exceeds k, the largest element is removed to keep the heap size bounded. The heap is then sorted and returned as the updated list of sums. For initialization, the sums list is initialized to the first row of the matrix, as these are the only sums possible by selecting one element from the first row. 5. Iterative merging. For each subsequent row in the matrix, the current sums list is merged with the row using the merge_sorted_sums function. This efficiently narrows down the possible sums to the smallest k at each step. 6. Final result. After processing all rows, the kth smallest sum is retrieved from the sums list at index k1 due to zero-based indexing and returned. ### complexity analysis. Time complexity. For each pair of rows merged, the heap size is at most k, and there are n*m combinations to consider in the worst case. For m rows, this gives an overall complexity of approximately O m k log k. Space complexity. The heap size is bounded by k, so the space usage is O k. This solution ensures efficiency even for larger matrices, as it avoids generating all possible sums explicitly and instead focuses on maintaining the smallest sums dynamically. Here, we start by importing the necessary Java utility classes, which will help us handle collections and priority queues. The main method, kth_smallest, is designed to find the kth smallest sum in a matrix with sorted rows. To achieve this, we define a helper structure, a max heap implemented using priority queue with a reverse order comparator. This ensures that the largest elements are prioritized for removal, making it easier to maintain only the k smallest sums at any given time. We initialize our process with the sums of the first row of the matrix. This gives us a starting point, as each element in the first row is treated as an individual sum. From here, we iterate through the remaining rows of the matrix. For every new row, we calculate all possible sums by adding each element of the current list of sums to each element of the new row. Each of these intermediate sums is added to our heap. However, to ensure that the heap does not grow beyond k elements, we remove the largest element whenever the heap size exceeds k. This way, we efficiently track only the smallest sums across all combinations of the rows processed so far. The intermediate sums are then stored in a new list for the next iteration, ensuring that the process continues seamlessly. At the end of the iterations, the priority queue will contain only the k smallest sums from all possible combinations of the rows in the matrix. To retrieve the kth smallest sum, we simply return the minimum element from the heap. Since the heap is in reverse order, the smallest element represents the kth smallest sum we were tasked to find. This approach leverages the efficiency of heaps to maintain the k smallest elements dynamically, ensuring the solution is both time and space efficient given the constraints of the problem. To solve this problem, we start by initializing our sums with the first row of the matrix. For the given input matrix 1, 3, 2, 4, and k equals 2, the first row is 1, 3, so we set sums equals 1, 3. Next, we merge these sums with the second row 2, 4. Using a min heap, we compute all possible pairwise sums from the elements of sums and the second row. For example, we add 1 plus 2 equals 3, 1 plus 4 equals 5, 3 plus 2 equals 5, and 3 plus 4 equals 7 to the heap. This gives us a heap containing 3, 5, 5, 7. Since we only need the smallest k equals 2 sums, we extract the two smallest elements from the heap, resulting in sums equals 3, 5. The process involves limiting the size of the heap to retain only the smallest values, which ensures efficiency. Now that we have reduced the sums to 3, 5, we can directly return the kth smallest sum. Since k equals 2, the kth smallest sum corresponds to sums, k1, which is sums, 1 equals 5. Therefore, the output for this example is 5. Moving on to a larger matrix, consider the input 1, 10, 20, 2, 5, 8, 3, 6, 9, with k equals 4. Here, we start by initializing our sums with the first row, so sums equals 1, 10, 20. Then, we merge these sums with the second row 2, 5, 8. Again, we compute all pairwise sums using a min heap. For example, we calculate 1 plus 2 equals 3, 1 plus 5 equals 6, 1 plus 8 equals 9, 10 plus 2 equals 12, 10 plus 5 equals 15, 10 plus 8 equals 18, 20 plus 2 equals 22, 20 plus 5 equals 25, and 20 plus 8 equals 28. After adding these values to the heap, we retain only the smallest k equals 4 sums. The heap after merging the first two rows contains 3, 6, 9, 12, 15, 18, 22, 25, 28. From this, we keep the smallest k equals 4 sums, resulting in sums equals 3, 6, 9, 12. Next, we merge these sums with the third row, 3, 6, 9. Again, we calculate all pairwise sums. For instance, we compute 3 plus 3 equals 6, 3 plus 6 equals 9, 3 plus 9 equals 12, 6 plus 3 equals 9, 6 plus 6 equals 12, 6 plus 9 equals 15, 9 plus 3 equals 12, 9 plus 6 equals 15, 9 plus 9 equals 18, 12 plus 3 equals 15, 12 plus 6 equals 18, and 12 plus 9 equals 21. After adding these combinations to the heap, we limit it to the smallest k equals 4 sums. The heap now contains 6, 9, 9, 12, 12, 15, 15, 18, 18, 21, and we retain sums equals 6, 9, 9, 12. Finally, the kth smallest sum is sums, k1, which is sums, 3, equals 12. Therefore, the output is 12. In this final example, we handle an edge case where the input matrix has only one row, 1, 3, 5, 7, and k equals 3. Since there is only one row, we initialize sums directly with this row, so sums equals 1, 3, 5, 7. Since no merging is needed, the kth smallest sum is simply the kth element in this row. For k equals 3, the kth smallest sum is sums, k1, which is sums, 2, equals 5. Thus, the output for this example is 5. This demonstrates how the solution adapts to different matrix sizes and configurations, ensuring correctness and efficiency even in edge cases. To analyze the time complexity of the algorithm, let's break it down step by step. First, we initialize the sums with the values in the first row of the matrix. This setup involves simply iterating over the columns in that row, so it takes n time, where n is the number of columns. Now, for each subsequent row, the algorithm performs a merge operation to combine the current list of sums with the next row. If the current list has size m and the next row has size n, we would generate m asterisk in pairs of sums. However, since we are only interested in the smallest k sums, the algorithm uses a heap to manage this efficiently. Heap operations, such as inserting and removing elements, have a time complexity of O log k, and since we limit the heap to k elements, we perform these operations only k times for the smallest k pairs. Thus, the merging step has a complexity of O, min, m asterisk n, k, asterisk log k, where we are effectively avoiding unnecessary computations by using the heap to prune the results. Now, let's look at the overall complexity. The matrix has r rows, and we begin with sums initialized to the size of the first row, which has n columns. At each merge step, the size of the sums list grows, but it is bounded by k due to the heap size restriction. This means that for each of the R1 merge operations, the algorithm performs O, k asterisk n asterisk log k, work to combine the sums with the next row of the matrix. Multiplying this by the number of rows, the overall time complexity becomes O, r asterisk k asterisk n asterisk log k, where r is the number of rows, n is the number of columns, and k is the given parameter. For space complexity, the heap is the main contributor, as it stores the smallest k sums during each merge step, giving us O, k, for the heap. Additionally, the intermediate sums list also uses O, k, space. Since the input matrix itself is stored in memory, it adds O, r asterisk n, more space. Therefore, the combined space complexity so far is O, r asterisk n plus k. To complete the space analysis, we account for any additional auxiliary memory used during execution. This includes temporary variables and function calls, which are negligible compared to the primary contributors we've already discussed. Thus, the total space complexity remains O, r asterisk n plus k. When considering best, average, and worst-case scenarios, the time complexity does not change, as the algorithm must process all rows of the matrix regardless of their contents. However, the practical performance may vary slightly based on the distribution of values in the rows, since this could impact how quickly the smallest k sums are identified. Overall, the time complexity is consistent across all cases, ensuring predictable performance in most scenarios. To highlight the advantages of this approach, let's compare it to a brute force method. A naive solution would generate all possible sums by picking one element from each row, resulting in n to the power of r combinations. Sorting this enormous list would then take O, n to the power of r asterisk log, n to the power of r, which is computationally infeasible for large R and n due to the exponential growth. In contrast, the optimized approach avoids this blowup by using a heap to track only the smallest k sums at each step. This drastically reduces the number of computations, leading to a much more manageable time complexity of O, r asterisk k asterisk n asterisk log k. The improvement comes from leveraging the sorted nature of the rows and the efficient heap operations, which scale logarithmically with k. By focusing only on the most relevant sums, the algorithm achieves a practical and scalable solution for this problem, making it suitable even for larger inputs. Now let's discuss some common mistakes that can occur when solving this problem. First, not considering duplicate sums in the matrix is a frequent issue. When rows contain duplicate values, the same sum might appear multiple times. If we overlook this, we could end up with incorrect results when trying to identify the kth smallest sum. This is important because duplicate sums can lead to errors in indexing or counting as we traverse through the sums. Next, many solutions fall into the trap of using an inefficient brute force approach. This involves generating all possible sums and sorting them, which becomes computationally expensive when the matrix is large or when k is very high. This approach, with a time complexity of O, n asterisk m asterisk log, n asterisk m, simply doesn't scale well for large inputs. Lastly, one of the most critical mistakes is failing to leverage the fact that rows in the matrix are sorted. Ignoring this property means missing opportunities to optimize the search. To address this, a recommended approach is to use a priority queue or min heap, which allows us to dynamically generate and track the smallest sums efficiently. Another important point to consider is handling edge cases. For instance, if the matrix has only one row or column, or if k is greater than the total number of unique sums possible, the solution might fail or produce incorrect results. To avoid this, it's essential to validate the inputs and explicitly handle such scenarios in the implementation. Additionally, when using a heap-based solution, it's easy to mismanage heap operations. Mistakes like pushing or popping incorrect indices can quickly lead to logical errors. A good practice here is to carefully track the indices for each row and column and ensure that we stay within the bounds of the matrix. Attention to these details is crucial to ensure the correctness of the solution. This problem can be thought of as a variation of the well-known kth smallest element in a sorted matrix problem. The most optimal approach here involves using a min-heap to efficiently generate and track sums. Recognizing this connection can help you identify patterns common to heap-based problems, which often involve dynamically maintaining the smallest or largest elements. The fact that the rows are sorted is also key, as it allows us to prune unnecessary computations and focus only on the most promising sums. When considering optimization trade-offs, brute force methods are straightforward but inefficient, especially for larger inputs. On the other hand, heap-based solutions provide a balance between runtime efficiency and implementation complexity, leveraging partial sums and lazy evaluations. For extremely large inputs, more advanced techniques like binary search over the range of possible sums can be applied. While these optimizations can significantly improve efficiency, they require a solid understanding of concepts like binary search and sum counting strategies. This problem also relates to other LeetCode problems, such as kth smallest element in a sorted matrix, find k pairs with smallest sums, and find kth smallest pair distance, which can provide additional practice and insights. Let's briefly review some alternative approaches to solving this problem. The brute force method involves computing all possible sums, sorting them, and then returning the kth smallest. While this approach is simple to implement, its time complexity of n*m*log n*m makes it impractical for larger inputs. A more efficient alternative is the min-heap or priority queue approach. Here, we start with the smallest element from each row and iteratively generate sums while maintaining the k smallest sums in the heap. This method has a time complexity of k*log k and is well suited for reasonably large inputs, though it requires careful implementation. Finally, for very large inputs, a binary search on the range of possible sums can be used. This technique involves dividing the sum range into smaller intervals and counting how many sums fall below a given midpoint. With a time complexity of n*log max_sum min_sum, this approach is highly efficient but requires a deep understanding of binary search logic and methods for counting sums efficiently. Each approach has its trade-offs, so it's important to choose the one that best fits the constraints of the problem. Great job making it to the end. To summarize, we analyzed the problem of finding the kth smallest sum in a sorted matrix and discussed an efficient approach using heaps. Remember, this kind of problem is excellent for practicing matrix traversal and heap operations, which are both common in technical interviews. Thank you for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!